Okay, let's get started. So first of all, just a reminder, homework 4 is due, I think, on next Tuesday. And then we're gonna have the last homework assignment. And everyone should have a sufficient time to finish that. We don't have a final exam. Just be sure to submit your project, final project report on time. And then that's it. Okay. So let us continue with the neural network. At the end of last lecture, we introduced the formulation of neural network. We mainly use the feed-forward network as an example, right? So if you have taken my entry-level machine learning course, we talk about neural network instance by drawing a bunch of circles, and each circle represents a neuron, which actually is a number, right? And how those numbers are integrated together, do some kind of multiplication, summation, and nonlinear activation function to get into the each of the next neuron in the next layer, right? So here we're gonna use a more convenient yet a little bit more abstract notation, right? So we can view like each layer, the output is a vector, right? So at the very first layer, or we can call it zeroth layer, right? Is the input vector of the input vector is actually the feature vector, right? So suppose this is d0 by 1, right? And then we feed this vector to the next layer, which is actually our first layer, and then we compute a linear transformation of the x0, right? And then we do a nonlinear activation function, wisely over the transform the vector. We got output of the first layer. So we can view it as another vector, but now its dimension is d1, right? So you can imagine this W1 transformation matrix is of size of d1 times d0, right? And then you will feed the output of the first layer, x1, to the next layer. But again, we're going to first do a linear transformation through a second transformation matrix W2, and then do an element-wise nonlinear activation function. You get the output of the second layer, x2, right? So it is d2 by 1, right? You just keep doing this until you reach the last layer, right? If you want to get the output of last layer, you just need one transformation. You multiply the output of the second last layer, xl minus 1, right? By this transformation matrix X, you get XL. You don't need to perform element-wise the nonlinear activation function. This is just the tradition of the neural network literature, right? And then you will this guy, the output of the last layer of neural network as your prediction, right? And then to train this neural network, namely, we want to estimate the values of those transformation matrices W1, W2 to WL. We're going to feed our output to some loss function, right? For example, if you're doing regression, and a common use loss is square loss, right? So you're going to use your neural network to make the prediction according to every input vector. You compare it with the observed output, you do the square loss, right? You have n examples, you just take the average of this loss in predicting every example, right? So then there's a question, right? Once you get this loss function, and you know that given any input, right, every training feature vector, training input, you know how to perform this forward pass to compute your prediction, then compute the loss, right? And how do you minimize this loss, right? How do you optimize the weight parameters, right, to estimate this neural network parameters? So the most commonly used approach is called backpropagation. So why is it called backpropagation? Because the computation order is kind of like reversed as compared with the way you compute the prediction. So the way we'll compute the prediction is like, okay, starting from the input layer, x0, and then you compute the output of every layer one by one, right? In a forward fashion until you arrive at the last layer, you get the prediction, you get the loss, right? But when you compute the gradient of the loss with respect to each of those transformation matrices, we're going to use a backward procedure, right? So what's that backward procedure? Right? The idea is that I'm going to sequentially compute the partial derivative of the loss with respect to the output at every layer. So you can see that the outputs can be, you can view this as an intermediate result. Right? Because when you compute the neural network, you need to compute the output of every layer in this network, right? So we'll compute the gradient. We're going to use the chain rule to compute the gradient, or more rigorous speaking, should be partial gradient of the loss with respect to the output vector of every intermediate level, right? And to effectively leverage this, to compute this, right, we have to use chain rule, right? So that means when at any layer, right, if you want to compute partial L over partial XL, the gradient with respect to the output of the current layer, you need to first know the gradient with respect to the layer above it, right? L plus 1, right? And then because we know that XL plus 1 equals to sigmoid function of WL plus 1 times XL, right? So you know how you compute XL plus 1 according to XL. So now, according to the chain rule, once you get your gradient, partial gradient with respect to the output of next layer, then you multiply the partial gradient of the XL plus 1 with respect to the current L, then you can get your partial gradient loss with respect to the output of currently XL, right? That's the idea. Because you have to, if you want to efficiently compute this, you want to leverage chain rule. And if to apply chain rule, you need every step, you need the partial derivative, the partial gradient of the loss with respect to the output of the next layer. Then, according to the relationship between the current layer's output and next layer's output, you can apply the chain rule. Right? That's why the direction is kind of reversed. Right? Once you know the gradient of the loss with respect to the output of every layer, the computation of the gradient with respect to the weight matrix in every layer is straightforward. Right? You apply the chain rule again because your XL is computed based upon the weight matrix or transformation matrix in the current layer and also the output of the previous layer, right? So you can just apply the chain rule and calculate. And that's it. That's the key idea of the backpropagation, right? So in my introductory course to machine learning, right? So we take the wheel of the element wise, right? We want to look at, okay, for every particular weight value rather than weight matrix, how do you compute that? But if you view it in a more abstract way in the big matrix vector view, it's actually fairly simple. Okay, so we will not discuss the further details, right? The reason is that it's pretty trivial, it's pretty mechanical, and nowadays you never need to implement backpropagation by yourself, except in some introductory level courses and want you to understand every detail about this algorithm. But in practice, you never need to implement this by yourself. There are like a number of the libraries can do this very efficiently and automatically for you. So let us assume that, okay, we have some kind of powerful deep learning library or automatic differentiation library in hand. And you don't need to worry about the gradient calculation, those kind of details, right? And then we'll talk about, okay, based upon those libraries, how do we implement Bayesian inference or probabilistic inference for neural networks? Okay, any questions so far? Okay. So in addition to this quick review of neural networks and backpropagation algorithm idea, right? Another very important framework we want to discuss is called stochastic optimization. So stochastic optimization is kind of like a very classical topic in the optimization literature, but it just become popular like recent 10 years. The idea was proposed like maybe half a century ago, right? But its popularity arises with the big data. Because in the big data here, you find out that the deterministic optimization algorithm is really, really costly. Instead, stochastic optimization is very cheap and taking much less resource and working really well. That's why people, especially in the modern neural network model, right, in the big data scenario, by default, people will just do stochastic optimization. So what is stochastic optimization? So the basic problem formulation is that, okay, the objective function can be viewed or written or rearranged as an expectation of some kind of function, right? So this is our objective function, right? Theta is a variables that we want to optimize. Right? We want to either maximize this function or minimize this function, or in some cases it could be minimized. It doesn't matter, right? So suppose this is our objective function, right? The theta are the variables of interest we want to optimize. If we can reformulate this objective function as some expectation of some stochastic objective function. So stochastic objective function means that, okay, I have some g function. This is not a function of theta, which we want to optimize, but also a function of some random variable u. And remember, a function of a random variable is still a function, right? So that means this guy is actually a random variable. Right? And when we take expectation of this g function under P of u is actually expectation of this function g. So let us keep this general setting, because later we'll look at some concrete example to strengthen our impression. So if our objective function can be written as an expectation for some stochastic objective function, right? Then we can use stochastic optimization technique. So what is stochastic optimization technique? Right? So when we compute a gradient of our objective function, right? That means we're going to compute the gradient of this expected stochastic objective g, right? And under mild conditions, you can simply switch the gradient and the expectation, right? So that means you can first take the gradient of this stochastic objective with respect to theta, then you take the expectation under u. Right? Remember, this guy is still a function of u, so you still can take expectation under P of u. So if we can compute the gradient in this way, right? What does it mean? It means that the exact gradient can be viewed as an expectation of the gradient of the stochastic objective. In other words, you can use some stochastic gradient as some kind of unbiased estimate of the true gradient. And people would like to ask, okay, what if I just use the stochastic gradient to perform optimization? Will it guarantee to, say, find you some local optimum? Right? And the answer is yes, but under some kind of certain conditions. So as we just said, right, we can compute the stochastic gradient for the stochastic optimization. That means we just want to use the gradient of the stochastic objective g to replace the true gradient. Right? Of course, this is not an accurate estimation. It's just the unbiased stochastic estimation. So here is the general algorithm framework to conduct stochastic optimization. So first, we're going to initialize our variables, which we want to optimize data. And we can either do the random initialization or simply initialize them as 0. Then you're going to go through like big T iterations, right? For each iteration, you're going to randomly sample the random variables U from its distribution P of U. Then you can get an instance of your stochastic objective function G, right? You just plug in your sample U value into G, you got an instance of your stochastic function G. Then you take the gradient of the stochastic function G with respect to theta. You presume, okay, this stochastic gradient is a gradient. I'm gonna use that to conduct the gradient descent. I suppose we're minimizing the function, right? And then you finish one iteration. You just keep doing this, keep doing this, keep doing this until the maximum number of iterations, big T, are finished, or some kind of other stopping criterion are met. Then you return your current theta. That's it. This is called stochastic optimization framework. And here, we're going to decide for each iteration T, what is the learning rate gamma T or step size gamma T. But before we proceed to more details, any question regarding this framework? Because it's really very hard. Sometimes you're not able to get out there. Sometimes it is too costly to compute that. Yeah, that's a good question. That actually motivates this framework. Other question? But the algorithm framework is pretty straightforward, right? Yeah, okay. So next, we're going to briefly mention what's the guarantee of doing this simple stochastic optimization framework. If you have smartly designed your step size, sequence of step size, I mean gamma T, how it varies along with the number of iterations, right? Then this stochastic optimization framework will converge to some optimum, right? Sometimes some literature called local attraction basin, but whatever is you can roughly view as some local minimum, right? With probability 1 or almost right? Then what kind of a step size we should choose, right? First, we need to ensure that your step size gamma T are always positive. Second, the summation of the squares of the step size over T from 1 to infinity is bounded. So if I write it in this way, it should be gamma T squared is bounded. And third one is interesting one. If you don't take square, you just do the summation over all the step size from T equals to 1 to infinity, then it is unbounded. So third condition is this. That means it's diverge. So does this mean? I mean, intuition is like this, right? So the stochastic optimization is like, for example, this is your function local minimum, right? So stochastic optimization is like, okay, I'm kind of like a random jump and toward some local minimum. And if your step size is too small, like it decays so fast, it might converge before you arrive at any minimum. That's not what we want. That's why we require that the summation from 1 to infinite number of steps should be unbounded. Infinity means that you have enough, you're large enough to reach some local minimum or local optimum. Right? However, you also need to control your step size to be not too large. If it is too large, it could be just oscillate forever and not able to come down and arrive at some given local minimum or local optimum. So that's why you need to control that the summation of their square of the step size is bounded. So you can see these two conditions are, one is to make sure that your step size is not too small so that it won't converge too early before you arrive at any valuable local optimum, you just stop. And it cannot be too large, because too large, your update could be crazy and just oscillate quite a bit and never stop. That's the reason why you have these two conditions. And if you pick up a schedule that satisfies these two conditions and also the gamma t is positive, then we can show that with probability 1, they're gonna converge to some local minimum. Yeah. Yes. Yeah. So here we give some toy examples, right? Some very simple schedule, which both of examples satisfy these two conditions, right? And then we can proceed to the more modern schedule, right? And practice showing that learning rate is critical to convergence rate. Although you might have like a lot of choices of gamma t schedule, but smart schedule can make your learning way more faster than like ordinary schedule. Like even in theory, they're going to converge to some local minimum eventually, right? Asymptotically. So there are many works that develop learning rate schedules. And right now, like the mainstream of neural network learning is not just doing something like this. It actually introduced, they're enlightened by some physical process and develop some kind of momentum-based approach. Like for example, you're optimizing very long vector, right? For neural network, it might contain like 1 million factors. That means you're going to optimize 1 million dimensional vector. So they're going to calculate the learning rate for every element. So every element has a different learning rate or step size. And those step sizes are changed dynamically, not only depending on the current stack, but also depending on the previous quantity or measurement. You usually call that as momentum. So there are a lot of like momentum-based approaches. Like the most popular one should be ADAM right now. Most popular and robust one, but prior to that, there are also others. It's called Ada Grid and Ada Delta and etc. So there are well-developed libraries, and in most of the cases, you do not need to implement them by yourself. And even nowadays, like people find that, okay, if you just keep running ADAM, it still might not be sufficient. And sometimes like people will like, okay, I'm gonna run stochastic optimization for a while, right? And then I'm gonna reinitialize my stochastic optimizer and rerun it. And then you're gonna reset the learning rate, reset the initial step size, and go on. This is called schedule. If you look at the PyTorch package, they have provided quite a few different schedules. Sometimes someone is called Plato, sometimes it's called, I forgot. But anyway, if you're interested, you can take a look at it. Okay, any questions so far? So now let's relate this stochastic optimization to neural networks, especially in the large data applications. Why stochastic optimization is kind of foundation of modern neural network training. But the reason, one reason is that the data set is really large, right? So if you write down the objective function of neural network, it's typically a summation of the loss over a huge number of training examples. So n here could be like 1 million, could be 1 billion. And it's not on euro, right? Then you can imagine that, okay, even you can perform like back propagation for every example, right? If you want to compute one gradient, you have to go through 1 billion data points, all 1 billion data points. That's too costly. That's too costly. And knowing one gradient is only sufficient for you to update one step, right? That means every time you perform one step update, you're gonna go through 1 billion data points. That's kind of insane. That's too costly, right? However, if we can treat this objective function as a stochastic objective, expectation stochastic objective, things will become much easier. Right? Let's see how can we do that. Right? So we can partition the training data set into many batches. Right? Like, so for example, you got 1 billion examples, right? You can partition them into many batches of size 100, right? So you can imagine you got, like, so this is a huge number of the examples. These are their index 1, 2, 3, 4, 5, 7, right? You can partition them like you put every 100 examples. This is 100, this is 100, this is 100, right? As a mini batch. Then we can rewrite our objective function in this way, right? So this U here, index the mini batches, right? So this is the mini batch 0, mini batch 1, mini batch 2, mini batch 3, and you got N over B mini batches, right? B is the size of batch, size of mini batches, for example, 100. Right? Does it make sense? Right? So that means we can write our objective function as we're gonna first go over the index of every mini batch, right? And then inside each mini batch, we compute the loss function, right? Of course, the loss is still summation of the loss over every example in that mini batch. And then what's the benefit of doing this seemingly excessive double summation, right? So we can try to inside the summation of each mini batch, we can multiply a constant N over B. So the size of total data over the size of mini batch. Then in the outside, right? In the outside, when you do the summation over the mini batch, you got an additional factor, right? You need to cancel out this N over B, so you got B over N. Does it make sense? Right? It's totally the same as this guy, right? It's the same. And then this form will give us another interpretation of this objective, right? If you will U the index of the mini batch as some kind of random variable. So obviously it's a categorical variable, right? It can take values 0, 1, 2, 3, 4 until N over B, right? And assume that, okay, we're gonna assign some uniform distribution over U, meaning that U takes any value, right? K is simply B over N. Right? Then this basically means I'm doing expectation over this guy under U. Right? So the inner summation essentially is indexed by U, right? Remember, U actually is indexed on mini batch. So basically, the objective function or the loss can be written as I'm gonna take expectation over the many batches, right? And for each mini batch, we're gonna compute the loss, the summation of the loss over all the examples in a mini batch. Then I multiply this factor N over B, right? So if you try to recover this, right? So this is actually the summation of U takes different values, right? 0, 1, 2, all possible values you can take. And P of U times the corresponding loss, right? So it's a N over B and summation, blah, 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 computation over the loss inside this main batch, right? And we know that whenever in value you can take, this P of U is B over N. Remember, this is a uniform distribution, right? So B over N and N over B are just canceled out. So we will cover this double summation. Right? Does it make sense? Does it make sense? Any question? It's just some kind of trick of doing expectation over discrete and variables. Right? Okay. So now we arrive at a stochastic objective representation of our total loss, right? So it's basically, it means that, okay, when we compute the loss on the entire data set, we can view it, okay, it is expectation of the mini batch loss, right? And then we can use the cost optimization to minimize this loss, right? Minimize the total loss. How can we do that? Every time we first sample the mini batch index U, right? Then you just calculate the gradient of the loss under this mini batch. You use that as your stochastic gradient and update the model parameters. That's it. And what's the benefit of this of doing so? David. Yes, right. Because every time we only compute the gradient of the loss sum over a mini batch, right? A mini batch typically take 100 examples. You just need to calculate the loss for 100 examples, you can get a gradient. And you get one update. If you want to compute the exact gradient, well, you have to calculate loss for 1 billion examples. Sum over them and take the gradient. Of course, it's much more expensive. Okay. That's one motive. That's one motivation to use this cost optimization framework, because the modern data, the modern neural network, and the modern machine learning applications, you really have to use such a large amount of data, right? They don't want to spend too much cost to deal with them. So for each update, because we use stochastic gradient, we only need to access a small mini batch. Therefore, we can largely reduce the cost. Any question? Okay. So now we know the stochastic optimization framework, and bringing the basics of neural networks and the idea of the stochastic optimization, of course, also includes the motivation. Right? Let us look at Bayesian neural networks. So, what are the Bayesian neural networks? It's just the Bayesian version of neural networks, and that's it. So, we're gonna wheel the weights, namely those weight matrices as random variables rather than just a constant, right? Unknown constant. And then we place prior over those weights. We use different distributions to sample the observed output. For example, if your output is a continuous value, we might use Gaussian distribution, right? If your output should be some discrete variables like categories, right? And then we can use a Bernoulli or multinomial distribution, right? Or categorical distribution. Then that's the definition of Bayesian neural network. So let us look at some graphic representation, right? So we can view like, okay, I got my random variable W here, right? I have some prior over that. The given W, and given the training, given the input XN, I'm gonna throw this neural network calculation procedure, like forward pass procedure. We obtain our prediction, and given the prediction, we sample the observed variable Yn. So if you write down the joint probability, a joint distribution of your Bayesian neural network along with the data is like, okay, I'm gonna assign some prior over all the weights in the neural network. Then for every training example, we use some distribution to sample the observed output according to the neural network prediction. Does it make sense? Okay. So then the question is, what kind of prior should we use to place on the neural network weights? Most commonly used choice is just the standard Gaussian. Right? We can assume the prior distribution over all the weights of neural network is the standard Gaussian or diagonal Gaussian. Right? And in some cases, like if we want to learn sparsifying neural network, because small neural network is really large, we actually find out it's unnecessary to include so many weights, right? We want through some posterior inference, our neural network weights can be truncated, right? In this case, we can apply some sparse prior over the weights. For example, the spike and slide prior. The spike and slide prior is a kind of mixture prior. You have a spiky distribution surrounding 0 and a flat distribution, which is really a Gaussian distribution. Right? And then you got some probability pi to sample from this flat Gaussian prior. That means your weight is non-zero. And you have some prior probability to be sampled from this spiky distribution. That means your weight should be concentrated surrounding 0. Right? So this prior will encourage the sparsity of your neural network weights during the training procedure. And then given the prior of the neural network weights, right, how do we sample the actual data? Right? So we'll have a lot of choices, and the previously discussed distributions can all be used. For example, if your yn are continuous, you might just use Gaussian likelihood, right? If your output, your data is binary, then you can use binomial likelihood, and then you need to transform your neural network prediction into a valid probability, right? So I often use a transformation is just sigmoid function. This is similar to the logistic regression, right? Except that now our score is not just a linear transformation of input, it's just a neural network output. Or if you use if your output is a categorical variable, meaning that it's multi-class classification task, then you can use a multinomial distribution. But again, for categorical distribution, you have to calculate the probability of your y is 1 given yi sorry, it's not yi equals to 1, is the probability that your label belongs to ith label, right? And this score is usually obtained through the so-called softmax transformation, right? This is something we have discussed previously. Like if you want to do multi-class classification for a linear model, right? Your score is some you have to have several weight matrices, like W1, W2 to WK, and you compute the inner product between W1 with your transform feature vector, you get your score. For the first category, W2 transpose VAX, your score for the second category, WK transpose fix the case category. And then you need to apply the softmax to convert them into a valid probability vector, right? And then you use that probability vector to compute the likelihood. Okay. Does it make sense? Okay. And similarly, you apply the same thing here. Any questions so far regarding the formulation of the Bayesian neural networks? Basically, we choose some bar over the neural network weights. Most commonly used bar is just standard Gaussian. And if you want encourage sparsity, you might choose some sparse bar, spike and slab, or Laplace bar. There are a variety of bars you can use. And secondly, given the neural network output, you need to use another distribution to sample the actual output, right? Like Gaussian for continuous output and Bernoulli for binary output and multinomial distribution for categorical output. Okay. So now we have specified our model, right? Bayesian neural network model. The goal now becomes estimating the posterior distribution of the weights of the neural network. So how can we do that? And once we have the predicted distribution or posterior distribution of the neural network weights, then we can integrate with the predict likelihood, right, to compute the predictive distribution of your output given any test input and given data D. Right? This is just the standard framework of Bayesian prediction. So then the challenge task is how to estimate the posterior distribution of the neural network weights. Okay. So again, there are a variety of approaches to doing that. We're going to introduce a simple and popular method. It's called Bayes by backpropagation. And we're going to introduce a so-called reparameterization trick. And this is very, very useful and very, very popular. So before we'll talk about this Bayes by backpropagation, right? Usually, like people want to examine your quality, right, of Bayesian inference on your network. The golden standard is Hamiltonian Monte Carlo sampling. We mentioned that before, right? But usually it's too slow to be practical. Why? Consider that you got 2 million parameters on your network, right? We run your Hamiltonian Monte Carlo sampling. Remember, every time if we want to generate a proposal, you have to solve the equation, right? ODE, right? Very high dimensional ODE because you have so many parameters here. You got 2 million. That means you got another 2 million random variables. That's augmented random variables. Right? That's a momentum variable, right? And you solve this Hamiltonian system, which is 4 million dimensional. You use leapfrog. You run leapfrog for a bunch of steps, maybe 20 steps, or one sample. Right? And if you want your HMC working, you might at least generate like 100,000 samples, right? So you can imagine how slow it will be. Right? And to get rid of this, right? So we want to use the variational inference framework we have just learned. So how can I do that? In the Bayes by backpropagation framework. Oh, by the way, let's just quickly review what is variational inference. So variational inference is that, okay, I'm gonna assume or restrict a family of approximate posterior distribution, for example, Gaussian family. Right? So this is my true posterior distribution. I do not expect that I can get really close to or achieve the exact posterior. Instead, I'm just designate a family of approximate posterior, right? And then I'm gonna find out a best family member that is closest to the exact posterior, right? That's how variational inference, right? And this approximation family is called a posterior approximation family, right? And then this closeness is measured by the KL divergence, and we know that we cannot directly or explicitly minimize KL divergence, but we can equivalently maximize a variational evidence lower bound, right? Instead, and the computational variational evidence lower bound is really much easier. Okay, so now for the neural network, we need to first introduce such a approximation family. Right? The Bayes by backpropagation we are introducing now uses a fully factorized Gaussian. It's a very simple framework. Right? So we assume that, okay, I'm going to approximate the posterior of the neural network weights by a multiplication of individual Gaussian distribution over every element, or every weight element in your neural network. Okay. And each weight Wi is Gaussian is parameterized by mu I and some rho I. And here, why we use this log 1 plus exponential of rho I, because if we directly parameterize this guy, right, you have to add additional constraint that this guy must be positive, right? Now we just reparameterize it. Now reparameter, we just parameterize this variance in this form. Then rho I can be actual value. It can be positive, it can be negative. It doesn't matter, because you take exponential plus 1, take a logarithm, it always turn to a positive number, a valid variance. Any questions so far? It's pretty straightforward, right? Okay, and then we just use this fully factorized Gaussian approximation to construct a variational evidence lower bound. Right? So if we can recall, right, the variational evidence lower bound of the model evidence is actually an integral with this approximate posterior times the log fraction, right? Log fraction, which is the log of the joint distribution P of W and likelihood P of D given W divided by the posterior Q of W, right? That's the standard form. Right? And then if you do some kind of like arrangement and of those terms, you can see that our lower bound can be decomposed to 3 terms. The first term is this is summation over every weight element in your neural network. It is expected log prior of Wi under QWI, the Gaussian, right? Plus a summation over every training example. And we take expectation of the log likelihood of every training example under my posterior Q of W. And the third term is just the summation over the entropy of the approximate posterior for every weight element. Yeah. And then we want to maximize this guy, right? We want to maximize this guy with respect to QW. That means with respect to all those mu i's and rho i's. Right? We want to look at if there are any problem, like compute the 3 terms, optimize with these 3 terms, right? So the first one and the last one, they have the analytical forms. They have closed form. It's fairly easy to compute, right? Because this guy is standard Gaussian, right? So if you take logarithm of standard Gaussian, it's just some exponential, it's just some square quadratic square of Wi's, right? And you take expectation under QWI, which is not a Gaussian. It's really straightforward, right? And entropy of the scalar Gaussian has a closed form as well, which we listed here, so you can check it from Wikipedia. So the real challenge is the second term in the middle. We need to compute the expected log likelihood under our variational posterior approximation QW. We find that we actually do not have any closed form of this expectation. Why? David. Yes, because it's a neural network output. We can try to do some kind of concrete example. Like, for example, suppose my likelihood is Gaussian likelihood, right? So my log likelihood will be something like half minus yn subtracted by your neural network output square, right? We're going to integrate with my Q of W, right? Does it make sense? Right? And this Q of W looks nice because this is just a product of Gaussian. And mu I, vi, of course, vi is this guy, right? The problem comes from here. You want to compute the expectation with respect to the output of neural network. This guy is actually a highly nonlinear function. You can view it as the function of xn and w, right? But it's highly nonlinear function of w and xn. Why? Because remember, we first do some linear transformation over xn, nonlinear activation function, right? And linear transformation over the second layer, and nonlinear activation function. You do it layer by layer. You do this recursively, nonlinear transformation, linear transformation, so kind of stuff, right? So, and the final output G will be highly nonlinear to the weight matrices in this recursive computation, right? Then you integrate with a Gaussian. I won't give you any closed form. Does it make sense? If you still feel uncomfortable, you can try to write down the expression for, say, two-layer neural network and try to integrate with Gaussian by yourself and say if you can do it and later. Any question? Okay, so then now that we're not able to compute the exact form of this middle term, what shall we do? Relating to the stochastic optimization framework we just discussed, we come up with some idea, right? We can use stochastic optimization. Right? Because this is an expectation of some stochastic objective, right? And we can try to apply stochastic optimization. So this actually relates to a second motivation of using stochastic optimization, because some case you even cannot write down the explicit form of your objective function. So I mentioned two cases, right? One case is that, okay, your data is so large, the computation of your exact loss is so costly. Right? I don't want to do that, so I choose to represent it as an expectation of some stochastic objective. So I can apply stochastic optimization, right? And the second scenario is that, okay, maybe n is not that large, right? And maybe just 1,000, it's okay, right? However, because of this intractable expectation, you're not able to write down the explicit form of your objective function. In this case, you have to seek for stochastic optimization as well. Does it make sense? Any question? There we go. Yeah, you can do it. Yeah, definitely you can do it. But you have to come out with some very smart transformation of this guy, right? And to make it easily to compute and easily to derive, right? But here we're going to introduce a very straightforward and not need any like not need you to do any product, some design, right? Another question? Okay, great. So now let us think about how do we apply stochastic optimization to maximize this variational evidence lower bound so as to estimate our approximate posterior, right? So the key question to apply the stochastic optimization is how to compute the stochastic gradient for each expected log likelihood, right? So from our previous example, we might think of, okay, we just generate a sample of the neural network weights from our current posterior approximation. Then we just replace W by our weight sample and calculate the gradient of log likelihood under with respect to the parameters of the approximate distribution. I would ask, does it work? Or is it correct? So we want to compute the gradient of expected log likelihood with respect to the variational parameters, right? So theta here includes the mean and variance parameters for the variational posterior approximation, right? So a natural or intuitive idea would be, okay, I'm gonna move my gradient inside the expectation, right? I'm gonna first generate a sample of W from our posterior approximation QW, right? And so I substitute my sample for W in this stochastic log likelihood, right? And then I calculate the gradient and use that as my stochastic gradient. So I ask, is that correct? Or is it feasible? Is doing this feasible? Any thought? It seems convenient, it seems correct, but unfortunately, you might have noticed this mark here, right? It's totally wrong. But why is it wrong? Why is it wrong? Any guess? Why doing this is wrong? David. Dependency of the theta. Yeah, I think you point out some kind of dependency. Theta depending on what? Yes. Right. That's the key. So let us do a little bit more careful analysis, right, to see why we cannot directly do this. So as we mentioned, right, the idea we just discussed is that, okay, if you want to compute the gradient of this expected log likelihood, we might try to sample some W out of this QW, right? And then you replace W with your sample, and then you take the gradient inside of the expectation, right? And let's see if you're doing so, what kind of result you get. So first, this guy actually, the computation of this guy only needs W. Right? It doesn't need theta. Remember, theta actually is the parameter of each QWI, right? Mu I, some rho I, which is e to the power of 1 plus e to the power of this guy, right? So once you get the instance of W, right, there's no way you can find out mu I and rho I here. So when you shove your W hat inside here, you just compute it. And this term actually is constant to theta, constant to mu I and rho i's. So if you take the gradient with respect to them, it will simply give you 0. And then you can see that, okay, your stochastic gradient is simply 0, and you have no way to update your theta. Of course, the result is absurd. You must find out why. If you try to write down explicit form of this, we'll find the problem, right? So the expectation of the log likelihood under Q of W given theta essentially is this integral, right? You write down this integral, this is actually integral of this QW given theta times the log likelihood, right? The way we just done, right, is essentially to move the gradient over theta just in front of this log likelihood. However, there is another term in this integral also contains theta, which is QW contains theta. You cannot directly escape it. I mean, if you really want to do this, right? Of course, we can move theta inside this integral, right? But you have to apply the gradient over product to do this, right? You cannot directly compute the gradient over this guy, right? Ignore this guy, right? That's why you got absurd result. And there's some kind of work like telling how do you compute the gradient of theta, gradient of this product with respect to theta, right? And basically, you have to compute the gradient of Q W given theta times logarithm log likelihood, and also Q W given theta times the gradient of the log likelihood. Right? You apply the rule and you do a bunch of things. Right? And this is that's not the focus of our today, right? We're going to introduce another even simpler approach to address this issue. How do we compute the gradient of this integral? This trick or this method is called the reparameterization trick. So what is reparameterization trick? We can see that when we perform these things, right? Because the distribution with which we take expectation also contains or also dependent on the variable you want to take gradient. That's why you cannot directly move your gradient inside the expectation, right? So then a natural idea will be, okay, why not we just turn this expectation into some other expectation? That expectation is under a random variable whose distribution has nothing to do with theta. And then we can apply this exchange. Right? We can put my theta, gradient of theta inside expectation for sure. Right? Now, how do we fulfill this idea? We're going to re-represent the random variable W by theta and another random variable. And this another random variable comes from some standard distribution, which is independent of theta at all. How can we see this, right? So we want to get rid of the unknown parameters in the distribution under which we compute the expectation. How can we do that? If we take a look at our variational approximation, it is the Gaussian, right? So from this Gaussian form, right, we know from our basic statistics, this Wi can be represented as a linear transformation of a standard Gaussian random variable, right? So Wi essentially can be represented as mu I plus square root, standard deviation times some standard Gaussian random variable, epsilon I, right? Epsilon I comes from the standard Gaussian distribution. In other words, my W can be represented as a function of my theta and the standard Gaussian random variable epsilon. Does it make sense? And here, theta includes mu I and rho I here, right? And of course, if you write it, write all weights in your network, right? You can write it as the mu vector plus some diagonal of this variance, because it's like factorized Gaussian, and times epsilon. This epsilon comes from the standard Gaussian distribution, but this is like vector. Okay. So that means we can reparameterize the random variable W as a function of the theta, which is our parameters of the variational approximate distribution, right? And some standard Gaussian random vector epsilon. Does it make sense? Any questions so far? Because this is really important. Everyone's good? Perfect. Okay. So now if we take a look at my log likelihood, which is yn and fw xn, and yeah, this is my log likelihood. So this is a function of w, right? It's a function of my neural network weights, right? So now, because we can further represent my neural network weights w as another function of theta and epsilon, right? So that means we can represent as another function, which is a function of theta and epsilon, right? Because w is just a function of theta and epsilon, right? You compensate g with this t function, you actually got another function to represent the log likelihood, right? Everyone is comfortable? Okay, so now my expectation under Q of W this is my original expectation, right? Now that I can transform this function as a function of epsilon only, right? Now this expectation should be the expectation of H function under the distribution of Cascade, the epsilon, right? They are the same. Because in the previous representation, this is actually a function of random variable W, right? You take expectation, of course, you're gonna take expectation under the distribution of W, right? And now you re-represent it as a function of epsilon. So it's a function of a random variable epsilon. If you take expectation, you're gonna take expectation with the distribution of epsilon. Does it make sense? And these two expectations should be exactly the same, right? Because because these are the same random variables. Their expectation must be exactly the same, right? There are just two ways to compute their expectation, but they must be the same. But the benefit is that for the second expectation, the distribution you use to compute the expectation is a standard distribution, is a Gaussian distribution. It has nothing to do with theta, right? And now I can apply my reparameter. I can apply my stochastic optimization procedure. If I want to compute the gradient of theta under this expectation, right? I can safely plug in my gradient here, right? Right? Because P of epsilon has nothing to do with theta. Does it make sense? Any question? So now, if we want to take a more concrete derivation, they are listed here, right? So first, we notice that this guy and this guy is the same thing, right? My log likelihood is a function of W, right? Because W is a function of theta and some standard Gaussian random variable epsilon, right? So I can represent this log likelihood as a function of epsilon, right? And then their expectation is the same because they're same random variable. And for the former, if we take the expectation like under W, right? I mean, compute expectation with W's distribution, right? And for the latter, I'm gonna compute the expectation with the distribution of epsilon. And because the expectation the distribution we use is a standard distribution. Right? It will become much easier, right? So that means your original integral with respect to QW is now turned to an integral with respect to standard normal random variable epsilon. Then you calculate the gradient here, right? Is equivalent to calculate gradient of integral with epsilon, right? Because this P of epsilon is constant to theta, right? So that means when you move the gradient inside this integral, right? P epsilon is constant, right? We can just move out. So we can put P epsilon here. And you only need to take the gradient of the log likelihood with respect to theta. And that's it. Any questions so far? This is a very simple but very convenient trick, right? And you do some kind of transformation, you represent this stochastic stuff as a function of another independent random variable. Independent by independent, I mean it has nothing to do with the variables, the things you want to optimize. Then you do the stochastic gradient computation. It will be much more convenient because you don't need to worry about this guy. Does it have gradient with respect to theta? It is constant to theta. But again, if you feel a little bit uncomfortable about this, it doesn't matter. Try to sit down, spend like 10 minutes to derive all this, and you get it. Here, I just want to highlight the key idea. And then we can get this stochastic gradient descent, right, to work, right? So every time we can just sample an instance of epsilon, right? And then replace epsilon here with your epsilon instance, then you calculate the gradient of the log likelihood with respect to theta. You get the stochastic gradient, then you update theta accordingly. Any questions so far? David. Assuming you feel like this guy have nothing to do with theta, the output. Yes. So here you have already got some instance of W, right? So we know that W equals to T epsilon and theta, right? So epsilon, of course, right now you have replaced it by some instance of samples, say 0.5, 0.6, blah, 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 name it, right? So once you get this, right, what you can calculate is that because you can use backpropagation to calculate the log likelihood with respect to W, right? And then you apply the chain rule to calculate the gradient of W with respect to theta. That's it. And this is where you are going to apply the backpropagation. And this one, because it's just a linear form, right? It's pretty straightforward. Yes, yes, exactly. And you have a specific dependency between W and theta. Another question? Again, I mean, if you feel a little bit uncomfortable, it's normal. When I first read through this reparameterization trick, I feel a little bit uncomfortable as well. But what I did is just sit down and write down equations, then try to verify every step in the derivation, and I feel comfortable. Okay, so now we can look back at our evidence variational evidence lower bound and try to apply stochastic optimization framework to learn the variational approximate posterior distribution, right? So we're going to couple both the data partitioning trick and the reparameterization trick, right? So the first two terms, the expected log prior and entropy, they have a closed form. We don't need to worry about that. The K problem is the expected log likelihood, the summation of them over the entire training set. Here we assume the training set is still very large. So we're going to partition the training set into a bunch of mini batches, right? Then we're going to introduce some kind of mini batch index. We view this index as a random variable, so it follows some uniform distribution, right? It's discrete random variable. So you can write your expected log likelihood, summation of log likelihood as some expectation under the mini batch index and under this epsilon, right? This standard normal distribution. And inside this mini batch, you're going to compute the summation of the log likelihood and multiply with this factor n over b. And then, because now we have an explicit form of the stochastic representation of the objective function, right? And then applying the optimization is straightforward. Every time we're going to sample an instance of mini batch U, right? And sample instance of the standard Gaussian random variable epsilon, and then shove them into here, right? That means you're going to pick up the corresponding mini batch. You're going to replace your epsilon by your epsilon instance. Then you just run the back propagation to compute the gradient of this guy, right? And you obtain the stochastic gradient. You just update theta. So you can take a look at the algorithm framework. Like we initialize our data randomly, namely the mean and the variance related row i's, right, for the variational approximation of your posterior, right? And then you go through big T iterations. Inside each iteration, you're going to first sample a mini batch, right? U, right? Then you sample an instance of a Gaussian random variable, standard Gaussian random variable, right? Then you compute the stochastic gradient, right? Here, this alpha theta are just the expected log prior and entropy, which have a closed form. You just calculate, right? And this one, you're going to pick up the mini batch. You replace epsilon with your sample instance, so you are able to compute the gradient for every log likelihood inside this mini batch, and you multiply this factor to ensure your whole estimate, your whole stochastic gradient is unbiased, right? And then you use this stochastic gradient to update your theta. I just keep doing this until some stopping criterion is met, and finally you get your theta. That means you get your variational posterior approximation of the posterior distribution of your neural network. As we mentioned, right? Because you represent your output of neural network, your weights of neural network as a function of theta and epsilon, right? So if you want to compute the gradient with respect to epsilon, you're going to apply the back propagation first, and then you calculate the gradient of the weight with respect to theta according to this T function. Right? And once you have this Q of W approximate posterior distribution of the W, right, you can plug them into the calculation of predicted distribution. Right? However, to compute the predicted distribution, you have still to do this integral, right? So this guy is a Gaussian, and this guy is a Gaussian likelihood, but the prediction for this X star is still through a highly nonlinear transformation procedure, which couple W, right? So that means you're not able to exactly compute this. And then how do you get the predicted distribution? A commonly used approach is use Monte Carlo approximation. Right? You sample a bunch of W samples from your approximate posterior and shove them into this integral, and to approximate this integral, just the average of those sample average of the likelihood according to those predict samples. So here are some performance which we copied from the orange paper. It turns out that it's working pretty well. I compare with a bunch of point estimation approach, like stochastic gradient descent, with all kinds of tricks, like result regularization, with some dropout trick and dropout connect trick. Those dropouts is our famous trick invented by Jeffrey Hinton, right? And we found that the performance is kind of like very similar. Right? There is some kind of typical learning behavior. So if you use vanilla stochastic gradient descent without any trick, you can see that it converges very early, right? And this is error, right? This is a test error. But if you use the this by backpropagation method, you can see that your test error actually keep decreasing in this MNIST data set. So the X-based is kind of a comparable predictive performance test to those non-Bayesian approach. At the same time, because you can compute predictive distribution, right? You have additional ways to measure uncertainty. So that's why it is quite powerful. Okay, any questions so far? Great. Yeah, let's stop here today. See you on next Tuesday.